I will begin. I will try to begin. All right. Okay, well, I'll start. Heavenly Father, we thank you for this day. I thank you again for these students. Just ask that you just guide our steps today. Help us to, again, just glorify you in what we do. And just help us to understand a little bit more about your creation together this day, Lord. In my prayer, Lord Jesus. Amen. Let me start with example 1 here, which will be the thing we were working on at the end of class. Can you guys help me remember exactly what the situation was? What was this? Mass A was what? 10 kilograms. What was mass B?
5.
And this one is at rest, is that right? And this one is 10 meters per second. And then I said afterwards, they collide, and you've got V, the velocity for A, and the velocity for B, and we are trying to figure out how that went. All right. So I guess I could call this 2 and 2, and over here in my language from last time, VA1 is 10 meters per second, VB1 is 0. Okay, so you can try to solve problems that don't make sense, right? So I showed you that last time, that if you just try to make up something, try to say, oh, suppose we're in the situation that the velocity of one or the other, the mass, is a particular value afterwards, it may or may not make sense, right? In fact, the two things that we tried, they didn't make sense, actually, right? So, and the reason for that, as some of you conjectured, was there's just one possible outcome, right? There's not a whole host of them. And so the question then is, how do you figure out what is that possible outcome, right? And so here's how we do it. We have MA VA1 plus MB VA2 equals to what? Momentum's conserved, right? So because momentum is conserved, this is equal to MA VA2 plus MB VB2. I mean, we have to face the music. I mean, this is required. And I'm assuming that it's an elastic collision like we did last time, right? And so if we hadn't gone through if we hadn't taken the steps and done the algebra we done last time, the only thing I could write down right now would be what? 1/2 MA VA1 squared plus 1/2 MB VB2 squared, right? It's 1/2 MA VA2 squared plus 1/2 MB VB2 squared, right? This is this is elastic, the elastic condition. So kinetic energy 1 equals to kinetic energy 2, right? But thankfully, we don't have to work with that, right? Because I've already gone through the trouble of solving that. And what did we replace that with? What did we learn? We learned that we can trade this nonlinear equation in the velocity. We can trade this equation for what? This we can trade for the velocity of, there was supposed to be a 1 here. My bad. Oh, goodness gracious. What's wrong with me here? VB1, VA2, there we go. VB1, let me just a second here. Okay. So we trade this for VB1 minus VA1 equals to what? Minus VB2 minus VA1. In other words, we can trade this horrible equation for this actually very nice, neat, and tidy linear equation. What do you want to solve? I personally would like to solve two linear equations and two unknowns. That is much, much easier, right? And now that I've gone through that theorem last time, we can do that. Okay, so then what? Well, so this is totally general, right? This is what these equations I just wrote down here, everything I've written down here so far, this is true for an arbitrary problem in one-dimension elastic collision, right? Let's specialize to the case that we're looking at. So some of these things I've written are 0, right? So what are we actually up against for this problem? We're actually up against, let me put the numbers in and skip the units if you guys don't mind. Let's see here. So 10 times 10 equals to what? MA was what? 10 times VA2. I don't know VA2 yet, right? And then plus 5 VB2. That's one equation I have to work with. What's the other equation? This right here, right? So this becomes what? V minus 10 is equal to what? You know, VA1. VA1, what's wrong with me? Good gracious. 2, dummy. Me, not you. Let's see here. VA2 minus VB2. Golly. I think it's possible that writing the solution for mission 2 in Calculus 2 has perhaps used some of my mental facilities in the last day, because I solved all 45 of those problems since last night. That's a lot. That's a lot. What idiot assigned all those? I should have assigned less. My goodness. All right, A2. But I hope you learned. If you're in my Calculus 2, and if you're in Dr. Sperano's Calculus 2, well, don't worry. He'll make up for it on the test. That reminds me, I need to make my test harder. All right, anyway, Dr. Sperano's making me look bad, you know? Let's see here. So, yeah.
Why isn't the velocity squared in the blue formula?
Because 20-minute derivation last class. This is a theorem. This is a theorem. We worked this out last class. It took me a considerable effort. That if for an elastic collision, the relative velocity before is equal to minus the relative velocity afterwards, it is not obvious. You're not missing, I mean, you're not missing some like algebra trick there. It's literally a full board of algebra.
Okay,
Yeah.
I thought you were filling in one with right?
Yeah, no. So we good? I mean, so then what can I do? I can substitute that equation, right, into this equation. What's that give me? 100 equals to what? 10 times VB2 minus 10 plus 5 VB2, which gives me 15 VB2 is equal to 200, I think. I was about to get 0 there, and that was really going to make me angry. But yeah, 100 plus 100 is 200. Yeah. And so apparently VB2, we should make 200 over 15, right? And VA2 then would be, let's see here, 200 over 15 minus 10. Let me put some units on these answers before any other physics professors come in here and demand I be fired. Let's see here, 200 divided by 15. I mean, this is very bad. Very bad, very bad. So VB2, this marker's garbage, 13.33 meters per second. And VA2 is please tell me I've made a mistake somewhere. 3.33? Is this right? That feels wrong. No, this can't. Well, wait a minute. VA2 is. Okay. So the larger velocity is on the what? The smaller mass, right? Okay, so 13.33 times 5. So the momentum, it's about 66.67 kilogram meters per second on the mass B. And on mass A, we've got what? .3 kilogram meters per second. So there's a net total of 100 kilogram meters per second in the final scenario. So yeah, this is right. This is right. So there you go. So that is why I was not successful in just randomly making up an example at the tail end of that derivation, right? Because I had to do this algebra to find out what's even possible for the final velocity of this one or this one after the elastic collision. In other words, I can ask this question in the format, you've got, a 10 kilogram mass going 10 meters per second, you've got a 5 kilogram mass sitting there minding its own business, they hit in a one-dimensional scenario elastically, what's the velocity of the two masses after the collision? That is a reasonable question. I wouldn't say it's an easy question, but it's a reasonable question. Now, in contrast, if I give you an inelastic collision, I can make up all kinds of scenarios there. And for the most part, if I'm careful, they're going to be reasonable. So like, check this out. So suppose you've got, I don't know, a baby. All right, and that baby is a 5 kilogram baby. All right, and you got an elephant. I can't spell elephant. How do you spell elephant? Is that right? Like that? Okay. How much do you want the elephant to weigh? 200 kilograms? No, that's 2,000 kilograms. All right. All right. So let us suppose that the elephant collides with the baby. All right. Maybe I should read. This feels. This is good. This is good.
Oh, I like it. It's better than murdering cats.
All right. Now.
This is more realistic.
Okay. So I will not assume a. Let's suppose that so let's call this one A, and let's call this one B. All right. And let's suppose that the elephant initially has a speed of 2 meters per second. All right. And the baby, of course, is at rest. And then afterwards, right, the elephant picks up the baby on its trunk. Baby's fine. Baby's fine. Don't worry. So the elephant scoops up the baby in its trunk, and in the process of doing that, that's not what I want to say. Rats. I want to say that sorry, I have to be more violent. The elephant whacks the baby, and just after the elephant whacks the baby has a speed of VB2 10 meters per second. Don't worry, there's like something cuddly it can fall into over here. It's going to be fine. All right. So then the question I have is, what is the velocity of the elephant right after this collision? Right. So how do you solve this one? And then I'll ask a follow-up question. Is this a elastic collision? All right. What's that? The condition of the baby? It's having fun. The baby's happy. It's an adventurous baby. It likes to be hit by elephants and set flying. Let's see here. This is the same baby that climbs the refrigerator when you're not looking, you know? Okay, so here we go. MAVA. Let me just get straight to the point here. We have 2,000 kilograms, right, times 2 meters per second. This is the initial momentum, right? And the final momentum is what? The final momentum would be the mass of the elephant, which we're assuming is still 2,000, times VA2, which we don't know, plus the mass of the baby, which was 5 kilograms. Man, that's practically a newborn. This feels wrong. I'll make it 15 there. That's more, you know. We'll make it 15 kilograms there. That's better. Now it's more like a toddler, right? I'm not a monster. There you go. 15 kilograms. So 15 kilograms times 10 meters per second. So we can solve for VA2. What do we get? Whew, goodness gracious, here we've got 4,000 kilogram meters per second divided by, minus rather, 150 kilogram meters per second. And then I got to divide by 2,000 kilograms. What's that give me? What is the velocity of the elephant after he knocks the baby? 1.925? That sounds about right. Meters per second, right? Question, is this an elastic collision? Yes. The answer is no. This is not an elastic collision. The relative velocity before, right? You could say velocity of elephant. So let's see here. The velocity before VA1 minus VB1, if you will, that was 10 meters per 2 meters per second, right? What's the relative velocity afterwards? So what's VA2 minus VB2? What's that equal to? Apparently, it's 1.925 meters per second minus, what was it? 10 meters per second. So the relative velocity afterwards is, well, minus 8.075. And as you can see, these are not the negatives of one another, right? It's not like we have minus the relative velocity before equals to the velocity afterwards, right? But that is a necessary consequence of it being elastic. Since that didn't happen, it's not elastic. The other way you could check if it's elastic or not, which would be more work, but sort of more obvious and logical, is to just calculate the kinetic energy before and compare it to the kinetic energy afterwards, right? And you would see that they're not equal. What do you think? Should the kinetic energy be more or less? I think it's probably going to be less. Right. Example 3. Suppose you've got elephant 1 going 10 meters per second this way. You've got elephant 2 going 20 meters per second that way. All right? And let's suppose that they have equal mass for the sake of discussion. Right? And then I tell you that they collide, and afterwards what happens somehow is that elephant 1 is at rest, and elephant 2 is going, 20 meters per second this way. And then my question is this possible? Is it possible for that to happen? Why or why not? Could you have a collision like this? The answer is no. The reason for it is pretty simple. if you look at the net momentum before the collision, you'd have what? You'd have like the mass times 10 meters per second, right? Minus the mass times 20 meters per second, using left as negative. So the net momentum is what? Minus mass times 10 meters per second, right? What's the momentum afterwards? Yeah, afterwards, the momentum would be mass times 20 meters per second. And of course, that is not equal to the momentum before, right? So I said this is a collision, so almost essentially by definition, in collisions, momentum is conserved. Momentum's not conserved in this example, therefore, that can't happen. All right, so anyway, enough about that, yeah? Let me take a second here to look at the solution to the homework you guys just turned in. If you guys don't mind, I'll find it eventually. So, oh, you got it. Here, I'll mess with it a bit. So I always wanted to talk about the pulley problem here for just a minute, because I don't feel like I've spent enough class time on that, and I know you guys already turned it in, so you're like, well, but I hope you learned something from it. Actually, I just wanted to take a look at a couple of these. This one, you might have done it a different way, but this is how I saw to do it, which is that at the top, the velocity is purely horizontal, right? So that means that the speed is just the x speed squared, right? So that immediately gets me to that equation, which tells me cosine squared is 1, which means cosine theta is plus or minus 1. So like, technically 45 degrees or 135 degrees would be reasonable. Of course, the 135 degrees is just the other way, right? I suppose there are other solutions which are physically unreasonable, right? Like minus 45 degrees, I don't recommend. You know, that'll also get you a cosine of 1, right? Oh, here it is, my laser. So here's how I saw to do problem 52. You might have done it a different way. And, well, anyway, you can look at this. Let me not talk about this too much in class here. Let's see here. But this one here, I thought I should just take a second to kind of sit and ruminate about. So, so the way I did this in the solution was I defined the position of the first mass, or the A mass, to be y, and the position of the B mass to be z, right? So then I can write down the potential energy before is MAGY1 plus MBGZ2. And then the kinetic energy is 1/2 MA plus MBV1 squared. Now I could write those separately, right? But there is a larger idea here, which is because the masses are connected by a string. Is there a question? Question? No? Because the masses are connected by a string, they have the same velocity, right? So that's kind of an important idea. And then when they just stop, right? That's when you have kinetic energy 0, so you just have potential energy, right? So then the other thing I had to notice was that if you look at the difference in the z's versus the difference in the y's, because there's a string that's connecting them, that means that the change in z is going to be minus the change in y, right? So I can write energy conservation. I can rewrite it in terms of the changes in y and z like this, and then I can change the z change to a y change like this, and then I can solve for change in y, which is actually what I'm trying to find, and I get this, which I know a bunch of you got that, right? But I bet you didn't quite do it the way I did it, did you? You probably talked about the length that it moved is L or something. It's fine, but here's another way to think about it. If it's, if you like it, great. If you have another way you do it, more power to you. And in a similar vein, this problem, again, I say, well, so like the y coordinate for this mass, the z coordinate for that mass, and it's moving to start with, and there's my initial potential energy. It's at rest at the end, which means we just have potential energy. And so then I multiplied this by 2 and divided by m, which gave me this. And then I rewrote it in terms of the change in y and the change in z. But in this case, you can relate the change in y to the distance up the plane according to the sine of the angle. So putting that in, I just get the length up the plane, which is I'm interested in, which I can solve for. And I got this, which I saw some of you guys got. So that's good. I hope you see that problem 56 was actually like stupidly easy, right? If you missed it, I'm sorry, but like figure out how to do that problem next time. And certainly on the test, don't miss that problem, right? That's a gift. And this one here wasn't bad once we make the simplifying assumptions that I did, right? So first of all, I told you, some of you, I think I made an announcement that the force is supposed to be the net force while it's in the barrel, which means that I can calculate the net. If I calculate the work done by the net force, that gives me, in this case, 100,000 joules. And then the work energy theorem says that oh man, son of a gun. That's supposed to be a 1. I made an error and I thought I'd fixed all of them, but I missed that 2. Curses. Anyway, so I got that as my initial speed, and then you feed it into the, and if you think about it, and then I said that the height of the barrel and the end position were the same, so that ends up giving me, whoa. That's a lot. 6,800 kilometers. Oh yeah, I think this is definitely outside the scope of the applicability of these equations, guys. Right? Why?
Because
yes?
at that range, the curvature of the Earth was such that if the plane was flat, then gravity would be at an angle.
This is one thing, yes. The curvature of the Earth probably... Wait a minute, the Earth is curved?
Oh, sorry, never mind.
Yeah, so the curvature of the Earth would matter. Yes?
It's going that fast because of that distance, air resistance would play much.
Oh, this is true. Yes, air resistance we should worry about, but we also lack the tools to make that argument precise. We need like a math 341, 334, my bad. We need differential equations and also a heavy dose of numerical methods to do that justice. But the other more basic physical issue here is that you're talking about a height which is probably high enough that F equals mg is no longer quite right. You have to go to the GMM over R squared thing we talked about to do it properly, and then you actually have to replace the mgh potential energy with the GMM over R energy formula. So that would also be in play if we did this properly. But anyway, you guys will get credit for that. That's cool. Yep. So there's this one. We talked about this before. And then, the other thing I wanted to say is I told the grader just to omit this, all right? So if you would like to, you can submit your work again in the next mission for this one. So we'll grade this one with the next mission. Because I gave you very unhelpful advice the other class, right? So, but it is solvable. I know there exists at least 2 or 3 students in here who have solved it. I'm not sure that they're right or not, but they had the same answer. So they're either working together or that's the answer, or both. And anyway, so you can try to do that for the next mission, is all I'm saying, all right? Obviously don't try exactly the way I showed you in class because that doesn't quite work, does it? So, all right. So let me talk to you guys a little bit about the rocket problem here. And get out of this browser. I'll try to go through this somewhat quickly. I'm more or less just going to read it with you and just talk about it because I don't think I have any homework on this precisely, right? Is there a rocket problem in the homework? I don't think so, but it's worth talking about for a minute. Now, Tipler is a book that we used for physics 231, 232 here for a couple years. It's a very good book, but it was, I don't know, just it's a little bit too hard for this course in some sense. But there's some very good discussions in here, and this is one of those. And so Tipler's like, suppose that you've got a mass and you've got this particle stream that's like either hitting the mass. So the particle stream either could be being ejected from the mass, or in this context, I think he's thinking more like a solar sail or something, where you've got, or a boat, maybe a sailboat, right? Or that's not the right thing to say. Something where the particle stream is hitting the mass and it's glomming onto it, right? So if you want to study the system, the mass is variable, all right, and it's changing because of the injection of new mass, which has a velocity with respect to it, right? So so in this situation, for small delta t, it's like the change in momentum looks like this, and he works it out, and he gets that it's based on the change in mass, the relative velocity, and let me just get to the point here. So he worked through this. He divides by, takes the limit as delta t goes to 0, and you see what you get is that the net force is going to be the mass that's there times the acceleration of that mass minus the change in the mass per unit time times the relative velocity. This is the relative velocity of the mass which is being ejected. All right, so this means that you get this modified Newton's second law, which is that the net force plus dm dt times the relative velocity of the ejected mass is equal to mass times acceleration. And so we can solve this differential equation to sort of understand the motion of a rocket, right? So if you talk to your parents later, you can be like, Mom, Dad, I did rocket science today. So there you go. Is that still like the gold card or the titanium? What is it? The platinum card of, you know, I'm smarter than you. I'm a rocket scientist. No, I don't know. Let's see here. So here we'll think about a rocket. It's got exhaust exiting at, I'll call it U exhaust, or you know, like that. And we'll assume that the mass is changing linearly with time. So we have an initial mass m0, and then it's burning off like a solid fuel rocket or something, all right? And I'm being really boring. I'm assuming that it burns it at a constant rate, all right? That rate is r. So dm dt is minus r here. The mass is decreasing at rate r. And so you start at time 0. You've got the, you know, initial mass m0, which includes the fuel load and also whatever, you know, kind of mass there is for the actual rocket, the cabin, all that good stuff, right? And so what's the net force on this? Assuming we're close to the surface of the Earth, the net force would just be minus mg j hat, right? Gravity's trying to keep it on the ground. And so the generalized Newton equation that I just sketched the derivation of looks like this: minus mg j hat, that's my net force. And then you've got mass times acceleration plus this changing mass term, right? Which, since dm dt is just r, it looks like this, r times u exhaust. So, so then, assuming vertical motion and vertical vectoring of the engines, the velocity of the exhaust would, of course, be like that, downward, right? You'd probably want your rocket to eject its, you know, fuel downward. I think that's safe to say. I mean, I guess we're not rocketing to the center of the Earth, right? With Godzilla and the rest of them, right? Like none of that. Have you guys seen the most recent Godzilla movie?
Yeah, they're all.
It's really something. It's got like, I think they put like the hammer of Thor in there somehow, like that hammer thing that they get with the blue stone or whatever. It's been a while since I saw this movie. All right, let me get back to the physics. So I solve for dv dy, and it gives me in this context r times the velocity of the exhaust divided by m minus g. Now this is a constant, this is a constant, this is a constant. That's, wait a minute, m is not a constant. M is a function of time here. The mass is changing, right? But the r, the u, the g, these are constants. And so then we separate variables, as you guys are all well aware of in your calculus 2, right? We've done this. And then separate, integrate, and okay, we can integrate this. It's just the reciprocal of a shifted, it's just a linear, 1 over a linear function of t. I put the t tilde here because I'm integrating from 0 to t, and I don't want to have the same meaning for this and that. Do the integral. You get this minus the natural log of that. So I plug in the time, and it gives me this. Properties of logs, I get log of the quotient of m naught over this minus gt. And so the velocity upwards of the rocket is, well, it's only upward if what? You do need what? You need that the product of the, you need that natural log of this minus to be greater than gt, right? Where did my u exhaust go? Is that a plus? Or is that a multiplication? Oh, that's a multiplication. I'm an idiot. There it is. So the product of this and that has to be larger than that, right? This is due to the thrust of the rocket, right? This is the ultimate, like, the contribution of the thrust of the rocket to the velocity is just this term right here, right? And so if that's not larger than gt, then you don't go anywhere, right? So actually, the first paper I ever wrote, I didn't realize I was writing this paper, by the way. So I had a junior laboratory. I was an undergraduate in physics at NC State. And my professor, Dr. Hans Holland, who was a lot of fun. So junior laboratory, we just kind of left free to do our own experiment for like the whole semester. You just make up something. And so we decided to do something called the Thomson jumping ring, which is, you know, this thing where you put a, are you guys in physics too, any of you? Wait a minute, you're in physics 1 right now, never mind. So you put a ring, right? You put a ring, hey, I didn't notice the contrast of Sam on Sam last class. So this is, I've established a pattern, so let's stick with it. Anyway, this Thomson jumping ring, you put a ring around a coil of wire, you make a current flow. There's something called, you know, induction that makes the magnetic field induced in the loop be opposite of the magnetic field induced in the coil, and because they're opposite, you know what magnets do, equal, you know, opposite magnets, they repulse, so the ring jumps, right? So it turns out like the existing literature on this hadn't factored in gravity. So this was the great, you know, analysis jump that my professor did. He put gravity into the situation to explain why, if the current is below a certain amount, the ring does not jump. So that would be kind of, this reminds me of it because it's the same thing. If you don't have enough thrust, your rocket just sits there and doesn't overcome gravity, right? So, but I say I didn't realize I was writing the paper because he asked me to do some research in the library. I wrote this, I like looked up some things and gave it to him, and then all of a sudden a couple months later we had a publication. I was like, what? Oh, thank you. And I was like, was that Saturday I spent in the library looking for things, was that really sufficient for background of that paper? I don't know, but it got published. So, but anyway, I'm grateful for that. We also had some liquid nitrogen to play with. At one point, my friend Jeff, he exploded a bottle outside using the liquid nitrogen somehow, and it made such a loud explosion that it made the campus security show up. Now, we were not there when they came, but they came. Anyway, liquid nitrogen's fun. Anyway, so supposing that condition is met, then this is only going to be this is only reasonable so long as you've got fuel, right? So once the fuel burns off, then you're done, right? At that point, the rocket is in what? It's in projectile motion, right? Which means that it's just under the force of gravity. And the time that you have for burning is the mass of the fuel divided by the rate. And after that, it's a free fall problem, like that. So, so just to put some numbers to it, suppose a Saturn V rocket has a mass of about 2.85 times 10 to the 6 kilograms. and the mass of fuel is about 73% fuel, all right? And a burn rate of 13.84, basically 13,840 kilograms per second. That's a lot. The force of the thrust is 34 times 10 to the 6 newtons. So then my questions are like, what's the velocity of the ejected matter, and how long does the rocket burn? What's its initial acceleration? And so I play with the numbers that and the formulas we've just been looking at, and I find that the rocket thrust is the velocity of the exhaust is actually at about 2.46 kilometers per second. That is that's a lot. It's fast, right? It would take about 150 seconds for that to burn. And what's the acceleration at time 0? The acceleration at time 0 is, doing all the math here, 2.119 meters per second squared, which is, like I said, kind of like throwing a Toyota into the sky. So now, for context, I think just when I wrote these notes, I think I had a Toyota Corolla at the time, and it was old. There are faster Toyotas, I understand, but you know. Anyway, so that's that. Do you guys have any questions about anything? Let's look at, in the time that remains, I think in your next homework there's a problem about there's a projectile motion where you have something explode at the top of the motion. How would you guys work that kind of problem? Let me suggest a slightly different problem than the one in the homework. And hopefully this will communicate to you some of the principles of how we solve such problems. Because it's a mixture of momentum conservation, but momentum's not just conserved blindly. Example 2, 3, example 4? I don't know, something like that. So suppose you've got a cat. All right, so you launch the cat with initial speed v naught equals to 100 meters per second. All right? And then, here, I'll give it a body this time. So you got a cat. And then at the top of the flight, right? Let's suppose at the top of the flight, the cat explodes. And so let's see, I need to describe the cat. It's got the head of the cat is let's say 2 kilograms. The body is, let's say, 3 kilograms, and the legs 1 kilogram. All right. It's a robot cat. Relax, people. Come on, not a monster. So at the top of the flight, the head of the robot cat goes flying upwards. The body of the robot cat goes flying downwards, right? So let's suppose that the head of the cat flies up at 20 meters per second, and the body of the cat flies down at 10 meters per second, all right? So then my question is, right after the explosion, where do the arms and legs go if they kind of stick together and all go in the same way? I'll draw them like this. So what's the velocity? What's this angle? Now the one in your homework I think is simpler because I just took a mass and I had it go up to the top of the flight, and then it split into 2 pieces, you know? I'm splitting this one into 3 pieces. What are the principles of solving this problem? What's that?
I said bury the cat.
Bury the cat. And then of course you can ask other questions like, where do the arms and legs fall? You know, after that. So what? But anyway, what's the velocity of the appendages of the robot cat right after that? Okay, so the way to do this. So first of all, is momentum conserved for the cat going from here to here? So point number one, momentum is not conserved in the process of the projectile motion. How is the momentum not, why is the momentum not conserved? The initial momentum, right? And so the initial momentum is not equal to the final momentum. Why? If I'm talking about up here. There's acceleration, yeah. So the change in momentum, right? Pf minus P naught, the change in P is what? It's equal to the net force times the change in time, right? Now I can't usually just say that, but I can say that when what? When the force is constant, right? What is the force here? Gravity, right? So the mass, total mass is apparently 6 kilograms, right? So yeah, and exactly, the net force is minus m total, right? G j hat delta t. Just an observation, right? The momentum is actually not conserved from the start of the flight to the top of the flight. However, we can conserve momentum right before and after the explosion, right? So that's what I would suggest we do. Because this isn't particularly interesting. I mean, we can work this out. I just wanted to mention this. So to conserve momentum a little bit more interestingly, we should look right before. And then right after. The explosion, right? So right before, what's the momentum? I'll call it P1. It's just mass total, right? Times the velocity. What is the velocity at the top of the flight? This you guys should already know. It's projectile motion, right? So yeah, it's just, I guess I need to give an angle, right? So I'll call it theta. There you go. So we would put the, V naught cosine theta 0, right? That would be the initial momentum. What would the momentum be after the explosion? So you got different pieces, right? You've got the what was the mass of the head of the robot? 2 kilograms, right? So you got your 2 kilograms. And what's the velocity of the head? 20 meters per second up, right? So I do 0, 20 meters per second like that, right? And then I have to add, I'll do this vertically if you guys don't mind. What comes next? I have to add, what's the body? The mass of the body was 3 kilograms, right? So I do 3 kilograms times 0, and what's the velocity? I said directly down, minus 10 meters per second, right? And then what? And then the part I don't know, right? The appendages. So the appendages, they're how many? What's their mass? I said 1 kilogram, right? So then plus 1 kilogram times what? Times the speed, which I'll call v, and then the direction vector of v, which would be what? Cosine, oh, I've used theta again, my bad. I'll call this, let me trade this theta for a alpha. So cosine alpha, sine alpha, we can figure that out. So you can solve this, you set the momentum equal, right? And look at it. If you know the value, if you know the value of the initial speed of the cat, right? If you know the masses that I told you, right? This is 6. then you can work this out. You have two equations, two unknowns. What are the two unknowns? The magnitude and the angle, right? Or if you like, you could swap this out for what? If you don't like this, you could also trade this for Vx comma Vy, right? And you could work out what's the velocity in the x and the velocity in the y for the appendages of the robot. And once you figure that out, then you could answer a host of other questions, like how far would the appendages fly from that point, right? Their initial height would be the max height of the trajectory. So that would give you that would give you an initial starting point for the motion. And you could figure out how far they'd go from there by our usual kinematics. Sorry, any of you friends with like a robot cat or something?
Yeah.
Yeah? A couple of them? His name is Stevie. Yeah, this is any discussion about robots and unreasonable affection of robots. It always reminds me of the Han Solo movie. And yeah, you forgot about it, didn't you? Yeah. Horrible, isn't it? Yeah.